Good morning. Thank you for letting me talk. My heart will always be glass. Unfortunately, my brain now is vision science. I will do as much as I can to weave in bits of glass here and there. And I want to say that because this is kind of outside everyone's area of expertise, if there's things I say that you want clarification on, I'd be happy to go over them later with anyone. So, because it's going to be more of a narrative than a science presentation, a little of both, I want to start off with an interesting story. 2 years ago, by chance, my wife and I met Bob Zeidman, who's kind of a guru in Silicon Valley. And just by chance, and I was wearing my Chroma company t-shirt, and he said, "Oh, I know that company, I have your glasses, I'm colorblind." And this happens to me a lot. It's pretty funny, but he told me this story that I want to share with you. So he was a freshly minted electrical engineer out of Cornell. First job working for a chip manufacturer in Silicon Valley. And he was going over a color-coded schematic. And he took it into his boss's office and he's like, I don't know, I can't follow this because I'm colorblind. And his boss was like, "It's your first day in the job in Silicon Valley, you expect to work here and you can't read color-coded schematics? This is a huge problem, Bob, because I'm colorblind too." And so he called over this engineer and he's like, "John, what are these colors?" He goes, "Beats me, I'm colorblind." And this is like an extreme example that Bob Zeidman shared with me, but it actually illustrates something that people are colorblind everywhere. Okay. There we go. So it's about 1 in 12 men and 1 in 200 women. Recessive, that's why women carry less. But the advantage to them is that as much as 25% of women might be tetrachromats, which means they have an extra dimension of color. And a professor at Oxford University has hypothesized that this is why men and women can't agree on decor. They just see it better than we do. And it's really hard to detect him because all the color vision tests are designed by men. Seriously. That's one of the big things. Okay. So, going back to Bob, because I'm probably the first person that a lot of adults have talked to who are color deficient, that knows something about it, they always want to confide in me. And what they want to tell me about is their childhood, going to school, what they experienced, how they adapted. And then I read this article that fully supported what they told me. This is a double-blind study. And in extreme examples, these researchers found that students sometimes get put into special education programs simply for being color deficient. And who are these people? The next, Rosalind Franklin's, Isaac Newton's. I mean, obviously, you survive, you adapt. So I got curious and I did a state-by-state reading of the state charters to find out who tested. Only 11 states tested, and I was really surprised by some of the people who do test. But again, there's really nothing that can be done even if you identify it. So, school, right? This is where it all begins. And there we go. I will get the hang of this. I'm a scientist. So, this is what's really interesting. Mark Zupan, who's the president of Alfred, made connection to one of his board region. This guy who's the CEO of Crayola Crayons. And it turns out, I got to talk to him. Turns out he's colorblind. And he did not know that in the vacuum of testing, that Crayola Crayons basically plays the role of color vision testing. Because the child draws something, the teacher's like, "That's not right." Calls in the parents to go to an ophthalmologist and have them tested and they're color deficient. But again, nothing that can be really done. It's really not really that much of an impediment. In fact, I was having an epiphany on this trip that there's some pretty interesting data that was done about 2 years ago on very low at threshold measurements of response to contrast and color contrast information. And there's this evidence that color deficiencies actually have a steeper function right at threshold. And it might explain why some really stellar quarterbacks, NFL goalies, and the world's top snooker players are all colorblind. That maybe color is not necessarily a great thing in certain tasks. Very curious. I can hardly wait to get back and talk to some vision scientists about this. This is very curious. So this is what it's like. This has been adjusted so you can see what a colorblind person sees. When I saw this, I was like, wait, is he running the right way? Because I actually thought there was a fumble, and he went, but no, it's just, and this is what they suffer through, and there's a lot of complaints to the programmers, like, you shouldn't have these jerseys that are indistinguishable, right? So my story, company's origin story, ties into sports and Silicon Valley, because coming out of Alfred, where I learned everything there was to know about glass from David Pye and Arun Varshnaya, I really did learn everything. I was so eager to go out and do my own thing. And after postdocing in New Zealand, I started a business in Berkeley, California, after 2 years working with Hoya Optics. And my customer was laser surgeons and laser eyewear companies in Silicon Valley. And this is like a frequency double gag, so 532 nanometer. And so I had these interesting glasses I'd made that were rare earth titanium borosilicates. And I could get as much as 50 mol% neodymium into these glasses. And I knew that it was unusual because the viscosity would go up, which tells me that the neodymium was acting as a glass former, totally breaking Zachariasen and Sons rules. But there you go. So I found out that the surgeons were borrowing the glasses and using them as sunglasses. And the reason they did this is they loved the fact that it helped differentiate tissue. Now, why did they do that? Because I was using neodymium, and I was primarily using this band at 530, 527 stark broadening to get an optical density up to 6 or higher in the eyewear. But this band at 580 to 600 was actually doing something really important. At the time, I didn't realize it. It was helping to differentiate tissue because it occurs at the place of overlap of your middle and long wavelength sensitive photopigments. So even somebody with normal color vision, creating more separation between those photopigment classes leads to greater contrast. And currently, 50% of the population has a longer L-cone polymorph that is evidence that that process is continuing. We're getting better color vision as time goes on. In fact, color vision deficiency is kind of a throwback to an earlier stage when we only had 2 photopigments and then the longer wavelength one mutated. So this is how it works. Light bounces off an object. It can be colored or achromatic. Enters the eye, interacts with the cone cells, creates electrical signal, goes to the ganglion cells. And these are like little calculators, and they calculate not absolute values of the photopigments. That's not how your color vision works. It calculates differences or sums. So your brightness channel is just the sum of your 2 longest wavelength photopigment quantum catches, right? And for one of the chromatic channels, which determines red-greenness, it's the difference. And for the blue-yellowness, it's the difference between the short wavelength, blue sensitive, and the sum of the 2 longer wavelength ones. So this is what the photopigments look like. And these are actual at the photopigment level. So you can see that the normal green sensitive and red sensitive cones overlap quite a bit. Again, because that's the red one is a mutation of the green one. It's still moving out. But these throwbacks, this is an example of someone who's moderate Dutan, where their M cone is acting more like an L cone. So it's shifted over, red shifted and overlapping. So imagine when you go to do that calculation, L minus M, you don't get a very good number. And that's where the confusion comes in. So This was the question that drove me crazy. Got it from journalists, color deficients, family members of color deficients, people who watch videos. How do you know your red is my red, right? And it takes literally, that 9-word question takes like 9 minutes to answer. So I'm not gonna do it, I don't have the time. But it can be answered now. So this is one of the things I did a few years ago. It's kind of interesting. We give out balloons with our eyewear, and the balloon colors are chosen very carefully to be what they call, but it doesn't matter. So anyway, we choose these balloons because they're really saturated when you blow them up. And this is kind of a simulation of what it looks like and where you'd expect confusion, right? Now the thing about this is about balloons is some shapes, some objects, you know the color, even if you're colorblind. Like, you know that says stop, you don't really need to know what language it is. Chlorophyll's green. A lot of objects have known colors to them, and a lot of objects don't. Like M&Ms, great to test with, kind of messy. I've used Legos and balloons, right? So this is kind of what you would expect. This is some data, and we got this data by watching YouTube videos. I literally just went through them, and the ones that weren't corrupted, I could use. So people end up naming them just sort of spontaneously. They name the balloon. What color are the balloons? They put the glasses on and they rename them. So this is the actual data. And what was surprising to me is that it's called red-green color deficiency, but they're actually pretty good at naming red and green. You can see blue and yellow. That makes sense because it's not affected. Sometimes they can confuse blue with purple because they suspect there's a purple balloon there, right? They can't see it, but they make a guess. But then they put the glasses on and they get them all right. But the one that surprised me was how the secondary colors, orange and purple, are the real confused colors. In fact, purple is confused with blue 94% of the time. Okay, so there's two types of color spaces I want to talk about. The one on the left is the one that everyone in this room is familiar with. It's how you determine a glass color, paint color, fabric color, on and on and on and on. The problem with this color space is it's a construct. You take the photopigments I showed you earlier, say the normal ones, and you multiply it by something called a color matching function. It's a complete constructed way to represent color. But you can then sum a few things and you end up with this diagram. And it's very, very useful for looking at things like chromaticity in a constant luminance plane, right? The problem is you can't compare color deficiency with color normals, except along confusion lines, which is not very useful. So this other map is a different way to show color. And this represents the color sensation at that ganglion cell level in the eye where the math is done. And you notice that's also divided by the luminance, which again makes it a constant luminance plane. This is a very useful way to represent color because you can compare normals to color deficiency. Why would you want to do that? Because you want to be able to design a filter and show that it's improving it, right? So that's what I did. So this is interesting. This is Jenny Boston's team at Sussex, and she did exactly that. First thing they did is they verified our model, which is what we do. 1, 2, 3, 4. Cones, spectra, illuminant, filter, sum them. You get some cone activity or excitation, and you can plot that in that space and say, well, this is what it looks like to be normal. This is what it looks like to be color deficient. And they did this really interesting test where they created this bipartite box. They put a target, filtered it with our eyewear. Color deficient looks at that and makes a match to these control swatches. And what they do is they end up matching to a more saturated, more true color. So you can demonstrate that they have pretty good color matching with the glasses on. Otherwise, they match to a very desaturated color, or too many of the swatches look the same and they can't tell them apart. So you can sort of verify the model and conclude that the information conferred by the chroma filters is usable for the visual system. Vision scientists never go out on a limb. That's like a very strong statement. That's about as much as they'll say. 2020, Jack Werner and Ken Knobloch, and this is Jack's student, Marsh Armstrong, did the thing that turned the tables and really showed people that our eyewear was improving the lives of color deficients, in spite of the billions of views of videos, people, there was still suspicion. Right? And what they did, they said, well, look at these photopigments, like this graph on the right. Let's take their difference, because that's what happens at the ganglion cell. So I looked at L minus M. There it is for normal, and there it is for color deficiency. Look, you've lost 60% of your contrast if you're protoanomalous, and 75% if you're deuteranomalous. Right? The luminance and the blue-yellow channels are unaffected. So you can see that in this right curve where they measure contrast versus D prime is just a scaling number, but it's basically the response function. You can see the top three solid lines are luminance response, and there's really no difference between color normals and color deficients. But if you look at the dotted lines, black is normal, red and green are color deficients. You can see two things. It takes more contrast before they see it. That's along the abscissa, right? And the rise on the ordinate is much less, maybe 50%. The test they do is on the left, and these are really cool. These are what they call Gabor patches, and they're sinusoidal Fourier patterns that you can alternate. You can basically change the relative contrast. This is a two alternative force choice test. Which of the two symbols on the bottom, the two patches, look most like the top? So that's your response. So they can then fit this to this Michaelis-Menten function, which has been around since 1911. Kind of amazing. But this sort of treatment of like, I'm going to show you something, what do you see, is how all of vision science is done. Oops, I went too far. Okay, so this is where it gets crazy. So what you see here is the control group at the top, over time, no change. These are color normals. You also see the poor guy who was deuteranomalous who was given a placebo at the bottom. He's the green line. He was really mad. Because he got into this study because he wanted to see what the world looked like. We gave him a care afterwards, but we needed him. We told him he was the most important data set. So, but look what's going on. These people's response max to contrast is improving over time without wearing the glasses. So they took the glasses home, they wore them, and they came back and got tested. I mean, that's remarkable. That's showing perceptual learning. Like, there's something going on that's so profound by this. And I actually said to some vision scientists a few years ago, I think this is going to be a great probe for us to understand how color vision works. Because the thing about testing children before it develops in the first 6 years, their color vision it's hard to like test because, well, there's HIPAA rules, but there's also just the issue around how do they communicate what they see, right? Very fungible brains at that age. So this came out in Nature Eye in January. This is confirmation. So this is really cool. This guy, Jeff Rabin, developed this test as a cone contrast test, very much like the test on the right, which is a visual acuity test that you're all familiar with. This measures the contrast between cone isolated colors that stimulate only one of your three photopigment classes, and where you can no longer distinguish the letter or name its color, that's an indication of your degree and type of color deficiency. So, on the left here you see that cone sensitivity. You can see that it's improved dramatically with wearing the glasses. And again, it's also improved without wearing the glasses after 12 days. And their color naming ability is also improved with the glasses and without the glasses. So this is the next thing I'm going to show you is absolutely amazing. This is a way to test cortical response. And this is what this method is called cone-specific visually evoked potential. So what you do is you show one of these screens to somebody with electrodes hooked up to the occipitus. And you're basically looking for a response. They don't have to say a thing, they don't have to push a button, they just have to observe. And very, very brief exposure, 1 to 2 seconds. And what you see on the left here, this is for someone who's a deuteranomalous color deficient. With no eyewear, you can see there's no visually evoked potential change. at V1 in the Visual Center. With the glasses, you can see there's a classic spike, and this is after day 11, continual wear, but maybe 2 hours a day, but without the eyewear. Again, we demonstrated, he has demonstrated that there's some perceptual learning, but now we can say it's at the cortical level. This is really, it's just the Helmholtz-Kohlrausch effect. People are color deficient. These are all equal luminance. And I really don't want to go into it, but it's basically saying that the glasses convey a brightness effect, that increased saturation leads to increased apparent brightness, but that's a color appearance model. Okay, so what do we know? Confers information, perceptual learning, improves memory color, which is what you have in your mind when you think it says, you say banana, you see something yellow, that's your memory color. The Helmholtz-Kohlrausch effect definitely improves the sense that the filters are lighted. We have a lot of complaints from people saying, I don't think these sunglasses are dark enough. And they're like, they're 15%. They're the same as Ray-Bans, but they seem like they're 50%. We're doing all of our work now in this McLeod cone excitation space. We have a pretty good system laid out where we can model improvement. This is typically what a spectrum looks like for an outdoor sun lens. You can see it kind of looks like neodymium, but not, right? And all the wiggles are to make it stable over many different light sources, because we want to keep it at the black body color. This is examples of the data we collect. This is 275 colors in that cone excitation space. You can see going left to right on the top, that going from normal to color deficient, that the whole field collapses. Things are not as saturated. On the bottom, you can see the same effect with the eyewear. So it's expanding it. In fact, what we do is we measure the standard deviation. It collapses, you get a smaller standard deviation, you improve it, the standard deviation goes up. And you can use this as a really effective tool. We don't want to change it along the S level, S direction, because that's where they have good color perception. So we're going to extend this to acquired color deficiency. Different disease, same pathology. No photopigment shifts, but a lot of noise in the system. We currently have I have a current pitch into the National Science Foundation for contact lenses based on a really clever chemistry that my chemists worked on. We have lighting solutions, already made it neutral over, but we're still seeking a partner. We've been interviewing people who haven't found it. We are working with a major American glass company to modify glazing in buildings. I mean, think about it. You're in a room, you want to stay alert. It's a retirement home, it's a child care center, it's a classroom, it's an office building. You want to be alert, you want to be able to look out at a beautiful world. It acts two ways, unlike glasses, which only act one way. You can look out and the light comes in. We're working with some Silicon Valley companies, I can't name them, but you would know them. They want to provide them for all their employees, whether they're colorblind or not, because they want to reduce injury on and off the job. And a lot of these things happen is like, because the CIO is colorblind and he drives with glasses and his life has changed, you know. And then he's like, I want everyone to have these. And we have this program called CAP. But this is kind of what you would expect, like you modify the lighting. The scene on the left of the pillar has been modified a little bit. I just did this in preview, it's nothing, you know, I didn't even use Photoshop. But just push the colors a little bit, you can see kind of like, that'd be a little more saturated. This CAP program is really cool. We're working, this is a partial list of the museums and gardens we have our glasses in, so people can go in and see art and flowers. We're working with universities. Alfred was the first to get on board. And we have there's a lot more big names coming online. And we work with a lot of school districts and with libraries, because they lend them out. And this is expanding all over the world now. We have some really big museums in Europe after COVID. This is the guy who's behind it all. He's our VP. If anybody is interested in doing anything like this, this is the guy to contact. See, like Tennessee has 13 parks now with viewfinders. And they had this video that's supporting tourism in Tennessee, and this guy came from Indiana. He's colorblind, and he said, he was wiping away a tear, and he's like, now I know what heaven looks like. And I was just like, oh my God, can't make that up. So now how do you answer that question, right? Well, peer-reviewed publication showing correct color naming, color experience is remembered, improved threshold and superthreshold color perception, evidence for perceptual learning, and the new information has made it its way as far as the primary visual cortex, which means it's most likely perceived. Thank you.